Good afternoon, everybody. Can I welcome you? I'm the President of the Institute of Physics. My name's Roy Sambles. It's a pleasure to welcome you all here this afternoon. For me, it's a real delight to introduce our speaker, Professor Eli Yablonovitch. He comes from the University of California, Berkeley, as the 2015 winner of the Newton Prize, Newton Medal of the Institute of Physics. It's a very prestigious medal, and he's a very prestigious winner. It's great to have him here with us. The award, as announced, it says is given for his visionary and foundational contributions to photonic nanostructures. Now, Eli is a scientist with a profound understanding of fundamental physical and engineering principles in photonics. If you see what we're doing, we're just talking about, he was saying, thinking of a way of extracting energy from the temperature difference between the radiation coming from the Earth and the black body radiation around us, the 300 or so Kelvin difference. Interesting concept, which we were just having a chat about. And if you can imagine, you could do that effectively, what it would impact upon our earthy ecosystem. He's got a keen interest, I say, in translating physics concepts into practical applications that address real, as I've just discussed, societal issues. One key area of his work has been the problem of solar cell efficiency, no surprise, which he first started working on in the early 1980s. Where he introduced what's called the 4n squared factor that describes the light trapping phenomenon applied in all high-performance solar cells. I think I'm right in saying that that 4n squared factor is now referred to as the Yablonovitch limit, which is rather good. The area I know more about, he developed the photonic bandgap concept, bringing together concepts from solid-state physics and photonics. That in itself spawned an entirely new area of research, now known as photonic crystals. Photonic crystals themselves have caused a real paradigm shift in photonics based on their ability to control the flow of light to an extent which most of us would have previously said was unthinkable. As a result, photonic crystals are now being used in research areas as diverse as quantum computation, nanoscale imaging and sensing, photovoltaics, optical interconnects, and high-performance light-emitting diodes. I also discovered, and I didn't know this, he introduced the idea that strained semiconductor lasers could have superior performance due to reduced valence bands hold effective mass. Almost all semiconductor lasers use this concept for optical telecommunications. In most computer mice, yeah, that's the right word, isn't it? For DVD players and in the ubiquitous red laser pointers. With almost every human interaction asked with the internet, optical telecommunications occurs by strained semiconductor lasers. So it's no surprise to learn that Professor Yablonovitch has received a substantial number of prestigious awards, as well as also having been elected, and this is somewhat unusual, a member both of the National Academy of Sciences and the National Academy of Engineering in the USA, while in 2013 he was elected a Foreign Fellow of our own Royal Society. So it really is, it's an honor and a great delight to be able to congratulate our truly visionary speaker, Professor Yablonovitch, once again, and to invite him now to deliver the Isaac Newton lecture. Professor Yablonovitch, delightful. Glad you could come. Over to you.
If I knew it was going to be such a great introduction, I would have started the recording earlier. Okay, it's a very great honor and a pleasure to be here. I am sharing with you some excitement that I have regarding science and a particular avenue of science. So what we have is an idea that dates back to Lord Rayleigh, and the idea is that you could have a periodic structure and waves that, let me draw the wavelength correctly, the waves that would come along would experience the periodicity and would experience reflection and would be totally reflected. Now, this was put forward by Lord Rayleigh. It's just very fascinating to look up the original paper. Actually, his paper, this is from PhilMag of 1887. His paper dealt mostly with parametric oscillation, and as an addendum, he added a few pages on periodic structures and how you can generate a forbidden band gap. And it has some rather peculiar properties in one dimension. But the curious thing, for 100 years after he put forward this idea, it bounced around. It was used in various areas, including X-ray diffraction and in other areas. But, well, this is actually the picture of some parts of the original paper coming out. And you can just see the way they published in those days. It was kind of remarkable. This photograph or this painting of him is a little bit different. But let me mention what changed. Oh, I should mention about the title. The maintenance of vibrations by forces of double frequencies. That's the parametric oscillation. He introduced parametric oscillation just like that. And he said, as an addendum, propagation of waves through a medium endowed with a periodic structure. And so this idea has been around since 1887, but it came as somewhat a surprise that to extend this into multiple dimensions had not been done. And I'll give you some of the motivation for doing that, but this step here, and especially here, is something that I stumbled across and was very surprised to learn that there were some very interesting properties when electromagnetic waves were going through these structures. So Rayleigh already figured out what happened when electromagnetic waves went through these types of structures, and it became very interesting to do it in 2 dimensions and also in 3 dimensions. But back in 1887, it was just in 1 dimension. And this extension to multiple dimensions occurred 100 years later. I proposed it, and Professor Sajeev John of the University of Toronto proposed the same idea. And so it's rather surprising that it took that long. And I'm not sure why, but maybe the motivation, the ability to make these nanostructures became more practical 100 years later. But there it was, and it led us to certain analogies between Maxwell's equations and the equations of solid-state physics, which are equations of periodic propagation of electron waves through a periodic structure. And what I've done here, I show you the periodic structure. That's a rather interesting one. But I've rewritten Maxwell's equations so they look a little bit like Schrodinger's equation with a little eigenvalue on the right-hand side. It's not exactly the same. It's actually quite different from Schrodinger's equation, but it is nonetheless an eigenvalue equation which can lead to forbidden gaps, just like we have forbidden band gaps in a semiconductor. And I had my motivations. I was working at that time at Bell Communications Research, which was a company that was supposed to do research in communications. And we heard about the importance of the laser for telecommunications. Almost all of our interactions with the internet occur by lasers. And the key to that is to have a laser, so you build up a population of electrons and holes, and you get lasing, but accompanying the lasing was just a spontaneous recombination of the electrons and holes. And this was regarded as an undesirable parasitic effect, which contributed to threshold current, and the lasers were less efficient and led to problems. And so what happened then is that I realized I could eliminate this spontaneous emission if I could have a forbidden region where the spontaneous emission would be suppressed. Actually, let me take a little digression. This is not part of the talk I was planning to tell, but I'd like to share with you a little bit what my thought process was at that time. There were a few papers written on controlling spontaneous emission, and it was all by analogy of, for example, putting an excited atom between metal plates. And in doing so, you could restrict the photon density of states between the metal plates. And that year, which was 1986, there were a series of papers published in Physical Review Letters saying that they were going to put dielectric mirrors, instead of metal plates, dielectric mirrors, and they called it a microcavity, and they could suppress spontaneous emission this way. And I looked at that and I said, wait a minute, the spontaneous emission is like jello. If you suppress it in the direction of the mirrors, it'll just squeeze out the sides. And so I thought, well, that just wouldn't work. So I said, to make it work, I would need to have, in addition to the periodicity associated with the vertical mirrors, so this would be typical vertical mirrors, and there was your light emitting substance, let's say some kind of quantum dot here. And it was certainly, the spontaneous emission would be suppressed by the mirrors. It couldn't go up or down, but you could go sideways. And there was no acknowledgement that the light could leak out sideways. So I said, well, that's no good. So I thought to myself, well, it's not a problem. We have periodicity in the vertical direction. Let me induce some periodicity in the lateral directions. And so I was thinking about how to do this. I said, well, I need some lateral periodicity, and I have there's some periodicity in lateral direction. Oh, that's not enough. I need the other direction as well. And I kind of looked at that, and it started looking a little bit like a checkerboard. And in this way, let's see if I can reproduce this exactly. I see it's not so easy to recreate my checkerboards, but we're getting there. Basically, it was clear that if you were going to have lateral periodicity, it would look very much the way a checkerboard looks, with all the red diagonals and all the black diagonals and so forth. And then I said, oh, checkerboard, that's very interesting. How do I build that into the third dimension? And I said, well, if you build a checkerboard up into the third dimension, it ends up looking like a face-centered cubic crystal. And then I said, aha, well, that's kind of interesting, face-centered cubic crystal. And then it became a little bit like solid-state physics. And I'll tell you in a minute how it ended. But we were able then to sort of come up with these structures. And if everything worked perfectly, the spontaneous emission would have no place to go, because you'd have coexisting. You'd have the electronic band gap of a semiconductor, which is taught to every solid-state physicist, but you would also have a band gap for photons, and as they would try to come out, they would have no place to go, and this would be a forbidden band gap. And that was a goal that I said, at the very least, it would be useful. It would be very useful for lasers and for other things to control spontaneous emission. That's the title of today's talk, is enhancing and inhibiting spontaneous emission. If I could suppress the spontaneous emission, the threshold current of the laser would go down, it would become more efficient, and that was the plan. But it was a rather difficult plan. Now, what made it difficult is that it had to be in 3 dimensions. And you can see how complicated this 3-dimensional structure is. In fact, it's rather odd looking, isn't it? And it was not clear what the structure should be. However, if you were in 1 dimension, what Lord Rayleigh had done, he had it all worked out. The 1-dimensional case was very easy, and he was then quoted, which I underline here. He had in mind an infinite laminated medium. That would be layers. So it was 1-dimensionally laminated. And he points out, and he has, by the way, the formula, this plus or minus represents the 2 edges of a band gap. So he has the correct formula for the forbidden band. But he points out in 1 dimension that you get total reflection even if you have a infinitesimal variation. Now let me see where here it is, the infinitesimal band gap. However slight the variation, this is the phrase I was looking for, however slight the modulation, you would still get a forbidden band gap in 1 dimension. And this was recognized at that time in 1887. Now, to do this in 2 dimensions and in 3 dimensions, the slight variation was insufficient. And I ran into trouble. I was looking for a structure that would have this property, and it was hard to find because we had no idea what geometrical structure would have this rather unique property, nor did we have any idea how much refractive index contrast would be required. I just showed you Lord Rayleigh said an infinitesimal contrast was sufficient, but only in 1 dimension. If you go to higher dimensions, you would need very substantial index contrast. And so it had its ups and downs. This was an editorial published in Nature saying, well, great idea, too bad it didn't work out. But John Maddox, he spoke a little bit too soon. We did eventually find a structure that had a complete band gap. This is actually the first experimental one. And it did require a significant index contrast around 1.9. And let me see if I can turn on the video here. And so this gives you a bit of an idea of how complicated looking the structure was. Let me speed up the video. And it is a rather strange looking structure, not one that you would think of. So the geometrical structure was, took actually literally years of trial and error. I was later criticized that I used the trial and error method when any self-respecting theorist would have just calculated it. But it's not an easy thing to calculate because it's like an inverse problem. You know what the goal is, but you have no idea how to arrive at the goal. And so it did take quite a bit of trial and error to get there. So this is kind of nice. And we were able to create a forbidden band gap in all directions, which could suppress spontaneous emission and could have some technical applications. So let me summarize then where we were at that point. We were applying solid-state physics concepts let's go back. We were applying solid-state physics concepts to Maxwell's equations. So we were unifying Schrodinger's equations with Maxwell's equations. Having a band gap was rather a big deal because it meant that there were no zero-point fluctuations. It was forbidden not only for real electromagnetic waves, but for the zero-point electromagnetic waves would be gone. So people got very excited. The quantum fluctuations would be absent. There would be no spontaneous emission. That's rather special, but I can tell you as sort of a practical person myself, it didn't seem like a lot of people were willing to pay me to get rid of spontaneous emission. In fact, they actually wanted to use light and wanted to do more useful things. So as it worked out, there were other applications. And I'll show you a couple of those. Actually, I'll show you just one application, which for the photonic crystals. But I'll show you what really happened to the field is that we came to realize that nature had discovered the photonic crystals before us. And that all over nature, there were photonic crystals and responsible for many things that are of interest to naturalists. And so I'll show you that in just a minute. First, I'll show you the technical application. This is an application that is used in silicon photonics. Actually, I'm the founder of a company called Luxtera, which is the pioneer in silicon photonics. And one of the problems they have to solve is that when you communicate over an optical fiber, by the time you reach the end of the optical fiber, there are so many twists and turns in the cable, you have no idea what the polarization is. And so you have to accommodate both polarizations. So we needed a way of coupling into this very narrow waveguide. We had a two-dimensional grating coupler where you had periodicity in this dimension, and this would send one polarization this way, and you had periodicity in the other direction that would send the other polarization this way. And this polarization diversity is essential in optical communications, is to be able to handle both polarizations. So this is actually used by Luxtera in their communications chips. They've sold over 1 million of these chips, and the business is going along reasonably well. As the data centers get bigger and bigger, they need more and more of these things. But that's the technical application. It's a bit narrow and specialized. I'll just show you what the product ends up looking like. This is not a USB connector. This is a more sophisticated connector that will take you up to 100 gigabits per second. And so great interest in computing centers and in data centers. And in this rather expanded plug, there's a conversion between the electrical signal and the optical signal, and the yellow cable is all optical fiber. So that's what the product looks like. And we're going to see more and more. You may have inadvertently used this if you just go to a data center. If you log onto a data center, download email, you could have inadvertently used a photonic crystal coupler to do that. However, what was more astounding is that not the technical applications, but that nature already knew about the photonic crystals, and they were found to be very common in nature. So let me see if I can show you some of those examples. And actually Roy Sambles is responsible for some of this type of research in all sorts of animals and in shellfish and in butterflies and in beetles and so forth, all of in the very colorful butterflies. We were very shocked to find that the colors are actually coming from periodic structures that were essentially photonic crystals. And here I have a series of there are many kinds in nature. So one-dimensional photonic crystals and two-dimensional photonic crystals. This is the sea mouse and this strange bird and not so strange peacock. These were all carefully investigated and discovered that the colors were actually coming from photonic crystals. In fact, if you see in nature a blue color or a white color, most likely it's coming from a photonic crystal structure. So who would have guessed that? Particularly in the case of the peacock, which is very colorful and used to be in the United States was the symbol of the first color television network, which was National Broadcasting Company. For many decades, they used the peacock as a symbol of great color, and much to my shock, that the color was actually coming from photonic crystals. The nature produces these nanostructures with these magnificent colors. Quite awesome. And in fact, those were two-dimensional photonic crystals. Then further study in nature was the three-dimensional photonic crystals, also contributing to color. And particularly this one is very interesting. This was the discovery made about 5 years ago. The diamond structure, although it's a great structure for Schrodinger's equation, it is also a great structure for photonic crystals. But it's very artificial, we thought, but then it was discovered in a beetle. And I've met the professor of the University of Utah who discovered this. I never thought we would discover diamond photonic crystals in nature. And I asked him, how did you make this discovery? He said, well, they were doing outreach to some high school students, and he had a high school student who had a beetle collection. And so he said, oh, that one looks extremely colorful. Let me analyze that one under the electron microscope. And he did, and he recognized it as being a diamond-like photonic crystal, which is rather a shock to me and to many of us. This is a sort of a close-up of this beetle with the diamond-like. The diamond-like is the optimal structure for a photonic band gap. And he even backed it up with calculations of the band structure, much as you would find in a solid-state book with the block wave vector and all this great stuff, but all part of the natural world. But there are so many others that have been discovered. And these are some of the birds, especially parrots. We know parrots are extremely colorful. The type of photonic structure that they have is more analogous. It's short-range order. It's not long-range order. And it is similar to amorphous silicon. This gives you a little micrograph of what structure is inside the parrot. So you have your 1D structure, your 2D structure, your 3D structure. The 3D structure, when it has the short-range order, it's not angle dependent. It's not iridescent. Iridescent means that it's angle dependent color, like in the peacock. But in these animals, it's independent. It looks the same from all angles because it is let's say microcrystalline with short-range order. Rather remarkable. This is an example of the macaw, which has been studied in great detail, and it has sort of an amorphous silicon structure. Rather amazing. Whoops. So let's see where we are. So I'm going to show you a few other animals, if I may, and let's see if this one comes up. So let's see what this one is. This is just published in the past year. It is the color changes in the lizard. It starts out green, and it does this by actually compressing the photonic crystals in the skin, and you can see it's gradually turning yellow. So it's a tunable color. And that part is rather remarkable. Should I show this video again? Yes. Okay. Let's show it again. And I cannot help but be amazed, because never did it occur to me that the research I was doing would have any bearing on the world of nature. And so it changes its color. That's the chameleon lizard changing its color. That they also have the same thing in reciprocal space. So let me show you the color change in reciprocal space as a proper solid state physicist. And there it is. So there they have investigated it in reciprocal space. But it's very interesting. They published a paper, but all these videos are available online. So it's the modern world of publishing. And so you get all these different colors. Okay. Well, it went on from that point. And I met an ornithologist from Yale University. This is a young man. His great hope in life, his great ambition, was to sit in a blind in the jungle and observe different kinds of birds. Let me show you what he observed with the bird of paradise. And this is the male, and he is trying to attract the female. Okay, and so there's a female comes along, and he's trying to attract her. And it's going along, and he's using a photonic crystal to attract the female. This is a great shock to me. So he's become a very famous biologist as a result of this, because he actually understands the physics too. So this is Professor Richard Prum from Yale University. So let's see. I think it was unsuccessful. This courtship happened to have been unsuccessful. Let's move on. So I wasn't so much interested in nature. I was more technologically interested. So we had the idea of suppressing the spontaneous emission, having simultaneously the very small wave vectors associated with the electron band structure. This would have been the electron band structure coexisting with the photonic band structure, which was a much larger wave vector, and the two would coexist. But it had its applications, but it's not really used this way. And it has other applications. And one of the issues was that you could suppress all zero-point fluctuations, you could suppress spontaneous emission, but mostly people want light, they want photons. And so what if instead of inhibiting the spontaneous emission, you could enhance the spontaneous emission? How to do that? And I regard, I'll tell you the way to do this, with an optical antenna. And I regard the optical antenna as the inverse of the photonic crystals, in the sense that the optical antenna enhances and boosts spontaneous emission, whereas the photonic crystal suppresses spontaneous emission. So let me give you an example, and this is a little odd. I'll indicate why on the next slide, but it's basically the idea is you have a light emitter, a quantum dot, a molecule, what have you, and the problem with spontaneous emission is as follows. And by the way, this is the 55th anniversary of the discovery of the first laser. And so ever since then, stimulated emission has been the king, and spontaneous emission has been looked down upon. And this is, there's a reason for this, and let me give the physical reason. The reason is that in order to get spontaneous emission, you have to store the atom in the excited state. So fine, you store the atom in the excited state, and in the excited state, actually as well as in the ground state, there are little AC currents flowing that are responsible for the radiation. But having successfully stored the excited state, then you need to radiate. And I say, well, that's no problem, the atom will radiate. Well, that's fine, but the atom is rather small, or the quantum dot, maybe it's less than 1 nanometer, and the wavelength it will radiate might be 1,000 nanometers. And so in order to radiate, it has to act as its own antenna. Now, everybody knows a good antenna should be half a wavelength in size. But atoms and molecules and quantum dots are far, far smaller than half a wavelength. They're perhaps 1,000 times smaller. So they're not very effective as antennas. And that's the reason why spontaneous emission is weak. Now, I can take it one step further. If you actually look into the theory of antennas, if an antenna is too small, the penalty will not be a factor of 1,000, it will actually be a factor of 1,000 cubed. So for that reason, Spontaneous emission is very, very weak, and when stimulated emission came along, everyone said, great, let's forget about spontaneous emission, that's the old stuff. But what happens in an antenna? Well, you tend to concentrate the electric field of the light waves. For example, you might have an electric field going from one end of the antenna to the other, and then you could concentrate all of that electric field into this narrow region, producing a much stronger electric field. So the electric field is enhanced according to how narrow this narrow gap is. And of course, what is the purpose of an antenna? Is to couple from wavelength size objects to objects that are much, much smaller than the wavelength. So antennas are inherently sub-wavelength. And they have been somewhat neglected since the discovery of the laser. So what is the problem of spontaneous emission? Is that the atoms are just too small to act as their own antenna. What if we would provide an antenna to the atoms and to the molecules? Then the rate of spontaneous emission could go up many orders of magnitude, as I say, according to the cube of the size. And so this would be kind of remarkable. It would be sub-wavelength, it would be spatially coherent, it wouldn't quite be a laser, but it would have many of the desirable properties. And so that would lead us to think, what if we could change the existing technology? If we look at light-emitting diodes, you can't modulate them very fast because the spontaneous emission is so slow for the reason I gave. No antenna. And if you compare it to lasers, well, lasers are very fast. People are very satisfied with lasers, 50 gigabits per second, 25 to 50 gigabits per second. So if we could, by adding an antenna to a light-emitting diode, we would have to accelerate the spontaneous emission by about 200 times, and it would become competitive with laser emission in terms of speed. And so this then becomes perhaps more interesting than suppressing spontaneous emission, is to enhance it by a big factor by adding an antenna to the spontaneous light emitter. You'd think this would be kind of an old idea. Before I get to it, I just want to show a system slide. So if you could do that, you could have an antenna, and you could use it in silicon photonics, and it would be better than a laser because it would not have any threshold current and would be inherently a low-power device. And then you'd send the signal along the waveguide, and you detect it with a small photodetector, and thereby you could perhaps go from where we are today from 10,000 photons per bit maybe to get to 20 photons per bit. So that's sort of the technical application for this. Now, the concentration of electromagnetic energy, people get very excited about doing anything sub-wavelength. And I say, wait a minute, we have been doing sub-wavelength for a very, very long time. And for example, you could just go back to the scanning tunneling microscope, which was a very sharp tip. It won the Nobel Prize, and you could get atomic resolution. But the resolution had nothing to do with the wavelength of the energy. It had to do with how sharp the tip was. And so there's this element that yes, you can go to sub-wavelength. Sometimes all it takes is a sharp, pointy object. But even if you were dealing with spheres, you would tend to concentrate the energy. And so from this viewpoint, it is not unusual to be sub-wavelength. And I can just pull out, as a prop, I can pull out my, my smartphone, and it is able to capture wavelengths, approximately 34 centimeters. It captures those wavelengths. It concentrates them onto a small transistor, which is perhaps a micron in size. So we've gone from 34 centimeters. So this, in technology, this would not be regarded as remarkable to be sub-wavelength. And often it just depends upon having a very sharp tip, or in the case of a cell phone, just a little wire, a little tiny wire, concentrate the energy down onto a little wire, and that's good enough. Now, who was the first to do this? Let's see. Was actually Hertz. And this goes back and brings me back to Marconi. My wife has been reading a biography of Marconi. Certainly a very heroic period. How did he make radio waves, and how did he make transmitters and receivers when there were no components available? He had one component that he used for everything, and that was the spark gap. He had some spheres, and he would draw a spark between the spheres by using a high voltage, and that was a step function in current, which step function could be Fourier analyzed into all frequencies up to radio frequencies. Okay, so he used that to generate the radio waves, and then to detect the radio waves, exactly the same thing. He had two spheres, and he drew a little spark between the two spheres, and that was his receiver. And yes, he was sub-wavelength. He was nonlinear, and in fact, from the very beginning of radio, it was understood it only works well if you have a nonlinear radio detector. So you needed to have this ability to concentrate the electromagnetic energy. Think about the frequencies he was using back then. A megahertz, 300 meter long wavelength, and he was all bringing it down to a little tiny spark. And he would look at these sparks. Somehow, one year he managed to transmit across the English Channel using those sparks, and then the next year he transmitted all across the Atlantic Ocean. So it was an incredibly heroic period back then. But I remind you, it was all based on sub-wavelength, nonlinear detection. And so that's rather remarkable. And in fact, this little thing was just the wire loop was itself just a little LC circuit. So it's rather unfortunate. We had the heroic period of discovering radio and how to make antennas. So Hertz, I believe, was the inventor of the antenna, but best exploited by Marconi. But if you try to learn about antennas as a physicist, and I had as good as physics education as I was told, you're getting the best education, young man, but I wasn't taught about antennas. And they didn't teach me much. There are certain things you ought to know, but you won't learn them from the standard books. So Jackson's electrodynamics, nope. And I've learned most of what I know from the Feynman lectures, still nothing about antennas, not Yari's books, and so forth. So there are a few important things to know about antennas that you don't find in books. And so I'll give you an example. For example, what is the cross-section of an antenna? It's actually, this is rather difficult to derive the cross-section. It's a complicated derivation, but it turns out to be a universal number. It's wavelength squared, and omega is the acceptance solid angle, but you could just say 4 pi. If it's an omnidirectional antenna, this just becomes 4 pi. So that's an important thing to know about. I'll just show you some examples of this in a minute, but I have to, if you want to make up for the fact that this is missing from all the standard electromagnetics books in physics, I did put a little tutorial in a paper I published at the beginning of the year. And the first 2 pages are a little tutorial explaining antenna cross-section, radiation resistance, and Wheeler's limit. These are like very super important things to know about antennas. Let me show you the first one. The capture cross-section of an ideal antenna. You'd think that people would tell you this, but it turns out to be independent. It doesn't matter if it's a good antenna or a bad antenna. It tends to be lambda squared over 4 pi. And this is true whether your antenna is something very professionally designed, or it could be a paperclip. So you have a little paperclip inductor, and but I don't know anything about the paperclip. I already know the cross-section. It's a rather universal number. And obviously the paperclip can be much, much smaller than the wavelength. It's still the cross-section is the order of a wavelength squared. And if it's a highly directive antenna, you can put in some other solid angle instead of 4 pi. So that's a kind of interesting thing to know. Here's something to know about antennas, and that is that this is something that you can figure out because you're told in physics radiated power is proportional to charge times acceleration. I was taught that over and over again. And since this power, I'm going to put in a square. So what is charge times acceleration? Well, I do happen to know the proportionality factor. And so here's my acceleration is in there, and this is my charge if I have a number of charges. And the time derivative, I can convert the time derivative into frequency because it's all sine waves. So I'll just take the time derivative and pull out a frequency. And I can go a little bit further. I can multiply and divide by the length of the wire. So this is the length of the wire. Multiply and divide by that. So now I have number of electrons per unit length times the velocity. So this is the number of electrons that are passing one point in the wire in 1 second. That's the current. So I can take this whole thing and write that as current. And I have a prefactor that is a bunch of fundamental constants. I have radiated power is proportional to acceleration, which is proportional to the current, and the prefactor. Now, based on dimensional analysis, the prefactor has to have units of resistance, units of ohms, because I squared R is power. So this whole thing in parentheses is called radiation resistance. It's one of the three important things to know about antennas, is the radiation resistance. It is, by the way, connected to the impedance of free space. So this is another thing that physicists, somehow they don't learn. I wasn't taught this because I was taught in CGS units. And this wonderful thing, the impedance of free space, which is made up of the most fundamental things, mu naught and epsilon, which also give you the speed of light. You think that would be very fundamental, and every physicist would know radiation resistance. They know the speed of light very well, but the radiation resistance, not so much. And part of the reason is, like me, they were taught in the edition of Jackson, where it was all CGS units. In CGS units, the 377 ohms turn out to be the reciprocal of the speed of light. So it doesn't look like anything, it just looks like the speed of light. But in MKS units, you see it is something rather different. So it's rather an important fundamental constant to me. Why is this less fundamental than the speed of light? It has the same two constants in it, mu naught and epsilon naught. But this turns out to be the impedance of antennas is related to the impedance of free space, sometimes divided by 2 pi. So this is the radiation resistance. In a very good antenna, it tends to be of the order of 50 ohms, and in a bad antenna, it could be of the order of 1 ohm. And you can make an equivalent circuit, like electrical engineers always want to make an equivalent circuit. There's effective, and there's some resonance, LC resonance, and there's some radiation resistance and ohmic resistance, etc. So you can do that. And then what is the problem? What if you have a bad antenna? If it's a very small antenna, the radiation resistance from the size, radiation resistance gets very small, only 1 ohm. That's a bad antenna. A good antenna is 50 ohms. What's the penalty? So curiously, the cross-section of the antenna still remains lambda squared over 4 pi. And the way you pay the price if you happen to make a bad antenna, in antennas, everything is opposite. In optics, we are usually aiming for a high Q. In antennas, we want radiation, so we want to have a low Q. So we want it to be as broad in bandwidth as possible, but if it's too small, you lose bandwidth. You still have the original cross-section. That's a universal number, this lambda squared over 4 pi. But the bandwidth gets to be very small. So one of the things I teach in the senior level electricity and magnetism course at Berkeley, I teach that every piece of metal the student has ever seen is an LC resonator. I pick up a metal chair and say, this is also an LC resonator. And every LC resonator is an antenna. And if it happens to be a very bad antenna, the penalty is in the bandwidth, interestingly. Okay, one more thing I should mention about this. The bandwidth then leads us to the radiation Q. So this is rather interesting. Where did this radiation Q come from? It's a rather interesting looking formula. It looks like should be a basic physics formula. And I see I don't quite have a slide for this. This is called the Wheeler's limit. This was figured out by a radio prodigy. So just like in this century we have computer prodigies, in the last century they had radio prodigies. His name was Harold Wheeler. This is not the Wheeler that was Feynman's thesis advisor, but it was a very distinguished gentleman. And he published this shortly after World War II, that there's a universal number for the radiation Q. And so with the students, I point out that their bodies conduct electricity, therefore they have inductance and capacitance. They have a personal resonance frequency, but they also have a personal Q. And in that respect, I'm not being fresh when I ask them, what is your personal Q? Okay, now how did I learn so much about antennas? Well, it was somewhat accidental. It was back in the period of the internet bubble. It was very easy to raise money for companies, and I convinced investors to invest in a company to make cell phone antennas. Honestly, I was motivated by the fact that none of my colleagues could explain to me how the cell phone antenna worked, and I thought of that as an opportunity. And we got our investment, and about 3 months after the company started, I said, oh my God, I understand nothing. I know nothing about antennas. And I went back to the investors and I said, you know that patent I told you was a great patent? It's probably not that great a patent. And would you like your money back? And then I discovered something that's very useful for us all to know. It is just as difficult to give money back to a venture capitalist as to give money back to the government. Have you ever tried to give a government grant back? They have no mechanism for this. The money goes one way. So, but they were very open-minded. They say, look, just keep working at it. You'll figure something out. And eventually we figured something out. First of all, I had to read all the antenna books. So what I've just described to you was synthesized from reading many antenna books. And the company eventually came up with an idea. It was actually a physics idea that made our antennas better. That took 4 years, unfortunately, but our antennas eventually were better than everybody else's antennas. And as a result, the company has now shipped over 1 billion antennas. And if any of you are carrying Samsung phones, you probably have our antenna in it. So I was pretty much forced to learn about the subject. Now, notice I give great respect to antenna physics. And I think they have their own beautiful physics. And you don't have to bring in plasmonics. You don't have to bring in the Purcell effect, local density of optical states. None of these concepts are relevant to antenna physics. You can imagine going up to an antenna engineer and say, congratulations on your excellent exploitation of the Purcell effect in the latest Samsung model. That's not the case. They would say they wouldn't know what you're talking about. Because many of these concepts are optical concepts. They don't really come to grips with antenna physics where these ideas are not needed. They have, in antenna physics, they have their own ideas like radiation resistance. Now, so I want to use the optical antenna to enhance spontaneous emission. And I'm going to make a rather extravagant claim that the spontaneous emission could be faster than stimulated emission. And how could this be? Well, the way to think about it is that there's a model put forward by Claude Cohn-Tanucci, the famous Nobel laureate. He put together a model for spontaneous emission. He said, spontaneous emission is just like stimulated emission, except that it is pumped by the zero-point fluctuations. So let's see what happens with an antenna. So I have some electric field that is coming in, and it's a plane wave, it's rather spread out, but the antenna will tend to concentrate the energy in this narrow gap. And if the gap is very narrow, I can build up a huge zero-point electric field. And following Claude Cohn-Tanucci, therefore, you have a very strong zero-point pump, and your spontaneous emission can become very, very fast. That's fine. Now, how can it be faster than stimulated emission? So let me show you how that can happen. So in stimulated emission, it's rather the same thing, except instead of being stimulated by zero-point fluctuations, you're stimulated by a real pump. Now, there's a limit to how strongly you can pump a molecule. If you pump it with a very, very strong electric field, you will destroy the molecule, distort it, you'll change all the energy levels. There's a limit, a nonlinear optics limit, to how strongly you can pump stimulated emission. And that limit is represented in technology. We know the laser can go 50 gigabits per second. They cannot go faster, because if it could go faster, they would. But nonlinear effects limit that. So there's a limit to how fast, how hard you can pump the stimulated emission. But what about the spontaneous emission? It's now pumped by zero-point fluctuations. They're kind of abstract, almost imaginary. When I was a student in college, the professor wasn't even sure that the zero-point fluctuations were anything other than a theoretical figment. But of course now we recognize them as being very real, but they are not going to destroy anything. The zero-point electric field is something that really, it cannot give up any energy. It cannot destroy anything. So we can concentrate the zero-point electric field far more than we can concentrate any real pump electric field. And so from that viewpoint, it should be possible for spontaneous emission to be faster than stimulated emission. And so that's what we're going to show. And that's the hope. Now, how does this manifest itself? Well, there's some strange things we teach physics students. But let me invoke one of them. You know how we teach in elementary chemistry? They say, oh, there are dipole fluctuations, and the neighboring molecule gets dipole fluctuations, and then they attract each other. says, wait a minute, if you have dipole fluctuations, that should radiate. Okay, so there's a bit of a paradox there. And in fact, you can look at quantum mechanics will tell you exactly how big the dipole fluctuations are. It's the matrix element. These are the AC currents that are flowing in molecules. Actually, they flow both in the excited state and in the ground state. And so what I'm going to do is I'm going to take those AC currents that are present even in the ground state, and but especially in the excited state, and they will those currents will induce currents along the wires, and I'll end up running current along the wires, and then I'll be taking advantage of an antenna, and I will radiate. Now the paradox, of course, is we teach this to freshman chemistry students, and there is a great paradox here. That is that if you believe those dipole fluctuations are real, where is the radiation? Of course, in the excited state, you're not surprised to get radiation, but in the ground state, this is something that Claude Cohn-Tanucci answered, is why ground states are stable, why they don't radiate. But that's a bit of a digression, but suffice to say, in the excited state, they do radiate, and you could just take this quantum mechanical current, and everything from that point on is classical antenna theory, with the radiation resistance, with the amount of current you start with, and so forth. And in fact, just as in real electrical engineering, where you might be starting with this quantum mechanical current, but eventually it evolves into a circuit diagram where you're taking into account all the effects. You might have some radiation resistance, you might have some ohmic resistance, all sorts of special things happen. And it's this physics, which includes metal physics, that's needed to understand how well you can do with antenna-enhanced spontaneous emission. Let's give you an example of one of the problems. Suppose we have an emitter, and it's right there. I hope you can see it on the screen. And it induces currents over a broad area because it happens to be rather far away from the metal surface. So the current is spread out over a big area. But what if, in the attempt to get a stronger effect, we bring the light-emitting quantum dot or molecule, we bring it very close to the surface, then the fields are concentrated into a very small area. And when that happens, you have a classical concept called spreading resistance, when you concentrate current into a small area, where normally it is thought of as putting a point on a semiconductor wafer, and then all the current has to spread away from that point. And so now we want to apply that to optical frequencies. That's one of the new effects. It's an extra resistance. In addition, there are other bad things. Anomalous skin effect, part of metal physics, but it has to do with a number of things, including especially surface collisions. All of these things penalize you in using the antenna. And in fact, if you look at it, you have the desirable radiation resistance, but you have different types of ohmic resistance come up. And some of these rise up to many ohms and prevent the antenna from being efficient, which is rather unfortunate. So there's spreading resistance accompanied by anomalous skin effect, etc., and there's ohmic resistance. So many bad things could happen, and we have to take all these things into account. So it brings us back to good old-fashioned metal physics. Now, one of the problems is, as you become more realistic about these effects, about these extra resistances, the efficiency goes down and down. So you could have a little LC model for your antenna. This would be a little LC model, and say, oh, wait a minute, I have a point dipole, and that tends to concentrate the current, so then I'll have spreading resistance, and whoa, wait a minute, I also have anomalous skin effect. Everything is pushing the efficiency down. So one has to be very careful. We can probably enhance spontaneous emission by a huge amount, but then the efficiency might drop below 50%. So I'm trying to get all my competitors in this field to agree we will stop quoting great enhancements unless they're above 50% efficiency. So that's one of the problems that comes up. And this is an illustration of the same thing. You could talk about 100,000 enhancement, but by then the efficiency would be less than 1%. So you have to be very careful in how you do that. However, one of the things you learn, probably 2,500 times enhancement is doable. So we have been doing experiments along these lines. One of the nice light emitters, it's not exactly molecule, and it's not 3D semiconductor, it's a 2D semiconductor. It's the monolayer chalcogenized, remarkable materials because they're a single layer, and unlike graphene, they are actual semiconductors. And we tuck these into an antenna structure, and we get tremendous enhancement of the spontaneous emission. And so the raw enhancement would be about 700 times. You can detune the antenna on either side, pull the resonance a little bit, but when you're tuned right on resonance, you do get a substantial enhancement. And when you take into account all the correction factors, it looks very much like 300 times enhancement has been achieved. And this is from these monolayer semiconductors. We've also recently, with my colleagues, Professor Ming Wu and his students, we've done electrically injected antenna LEDs. So this is with indium gallium arsenide phosphide, and where we do like conventional, electrode contacts P and N, and drive the whole thing electrically. The whole antenna is this little bump on metal surface. And by the way, that's all it takes. If you have a flat metal surface, just put a bump on it, that becomes an antenna. And indeed, it looks very much like we have a very significant enhancement parallel to the antenna axis. So it's getting there. We're looking at enhancements that are in the hundreds, and this is very promising. But we have quite a few competitors worldwide. Here's some work from Korea, very clever, using erbium ions, which are great light emitters. And so he's observed about 170 times speed up in lifetime. We have competitors at the Max Planck Institute for Light. This is a CAD selenide quantum dot, where they move the CAD selenide, they move it close to a sharp gold tip, and they claim about 330 times enhancement. So it's getting to the point where I think if we set the threshold 200 times enhancement, then you're faster than the laser. I think we're getting ready to claim that. Here's some recent work from Duke University. It's not a very good antenna because the currents tend to be concentrated along the metal surface and don't radiate, but there are some fringing fields out here that do radiate, and they have seen a rather large enhancement, but the efficiency unfortunately dropped a little bit below 50%. So what we're going to see in the next year or two, we're going to see tremendous enhancement from optical antennas, but we have to be very careful with regard to the efficiency. And so this is ultimately our vision, is to use an antenna LED, and it would be like a Yagi antenna with parasitic elements. It would direct the radiation into the silicon waveguide and would enable silicon photonics to go to the very short distances, whereas now it goes longer distances off chip, but now it might be able to go on chip. And however, we have to be realistic about the resistance, and that will drive the efficiency down when we take all those effects into account. But if you look at this calculation from the circuit model, it looks very much like 2,500 times enhancement should be possible before dropping below 50% efficiency. I want people to accept that as a ground rule. Maintain 50% efficiency. And so I think we're ready to claim that spontaneous emission is now faster than stimulated emission, and this is the factor 200 that we needed to, or 250 that we needed to surmount. And I think it's there. So it does represent a big step. So let me summarize, and that is that 55 years after the laser, we're still struggling with spontaneous emission. The first idea was to inhibit spontaneous emission, and that came from the photonic crystals. But I think the more modern idea is to enhance spontaneous emission. And it appears the way to do that, it's not a photonic crystal, it's the opposite. It's the optical antenna. And my assertion is that the optical antenna, it's another one of these things that's 100 years overdue. So we had Marconi, 103rd anniversary of the Titanic. Marconi said that his company became successful as a result of the Titanic. And now it's 100 years later, and we're finally applying antenna technology to light waves and rediscovering all of those things that Marconi knew. Thanks very much for listening.